great one today. We're actually, do you all know, how many of you are doing macroeconomics? How many of you love macro? Okay, hands for love macro. When I was an undergrad, I think I would have raised my hand. How many of you are like, kind of like it, but don't love it maybe? And how many of you despise it? Okay. Well, no wrong answer there. I don't teach macro usually. So today we're going to talk about Oken's law, if you're familiar with what that is. So we're going to talk about that when we get there. But we're going to use real data taken directly from the Federal Reserve. So I have two data sets. I'm going to show you how I downloaded them, where I got the data from, and then how I'm using them in the notebook. So I'm going to give you the data set that we're actually using, like the processed one that I've worked with. But I'm going to show you all the code to be able to construct it for yourself, which is something that you're going to be doing in your final projects. So we're going to come to this notebook here. I have a little bit of information, a link to where I got the data from. But we're gonna develop a model to address some problems we see in the data. What we're doing today, as it fits in with the rest of what we're doing in the semester, we started part 1 and 2 talking about how to summarize data, how to work with different data sets, how to transform variables, and all of this. The basics of actually processing data. Part 3, we talked about getting started with basic ideas in statistics, thinking about random variables, and then the central limit theorem, and basic hypothesis testing. Part 4 was the basics of the general linear model, which is what we actually use. And then part 5 is a bunch of more complicated applications of the general linear model. So last time, we worked through an example using fixed effects and interaction effects to look at the gender wage gap. This is one of my favorite things we've done this semester. We walked through and we built this idea of different intercept terms to capture essentially a two-sample t-test. But then we extended this idea to not only have different intercept terms, like we did with the two-sample t-test, but we can also check whether there are interaction effects or slopes. So, a relationship not just between levels, like difference in levels, but also whether there's once we control for the relationship between wages and education, is there actually a difference remaining? So we can include a slope in our two-sample t-test, or the equivalent of the two-sample t-test. So this allowed us to do something extra on top of a two-sample t-test simply by including a fixed effect. So we have our basic regression model, but then we allowed for a fixed effect to give us that difference in the vertical intercept between the two groups. So amazing thing we did. And then we also talked about the possibility of multiple slopes. So are there differences in the returns to education by gender? And so we walked through and we built this model. So we allowed there to be the possibility of two different slopes, one slope per group. And so what we did is we had an interaction effect on a second slope variable. So we have not just our beta 1 controlling the slope for our baseline, but also when male is turned to 1, we get a second slope. So an additional relationship between education and wages. And so we went through and tested this, and our null hypothesis in this case, the difference in returns to education by gender, the null hypothesis was that beta 2 was equal to 0. And so we walked through and built that out using code. And then the last thing we did was run a model that gave us both differences in the vertical intercept and differences in the slope. And we ran this model and plotted the results. This is a little bit more difficult to interpret, so we're not going to spend a ton of time on this interpretation. But some of you may kind of work with this kind of this model. So the way we would set it up is just we have Beta 0 gives us the vertical intercept. Beta 1 gives us the slope of the zero-coded data points. Beta 2 gives us the wage premium, so the difference on the vertical axis. And then beta 3 gives us the extra slope for the one-coded variables, one-coded data. So we have our interaction effect on the slope coefficient. So this is what we did last time, and we talked about the different types of questions we can ask with each of these 4 models. Okay, so this is one of the core extensions of the general linear model. We can do just really general things with this. There's a reason we call it general, because we can build just lots of different models. If you can draw some lines on a plot, you can build a regression model that does that. So what we're doing today is turning to a different kind of question. Often we have data that's related through time. And this presents some additional challenges which we're going to see in our data set. The motivating example for today is Oken's law, which looks like this. So just a picture of this. How many of you remember Oken's law from your, have you talked about this in macro? You have? In intro or intermediate? Intro, okay. Yeah, fair enough. I don't remember this from my intro macro class either. This may be a more advanced topic, but it gives us the relationship between GDP growth. So year after year, what's the percent change in GDP? So the output of an economy on the vertical axis. And then on the horizontal axis, we have change in unemployment. So this is not a percent change, but it's an actual just difference in the unemployment rate quarter to quarter. So what we're going to do is actually go to the Federal Reserve data, download it, and then construct this model. So we're going to construct all of this together. So I'm not a macroeconomist, but this is, I think, a pretty interesting application of time series data, which a lot of you probably will work with. All right. So the questions we're going to try to answer today, first off, it's nice seeing all of you. Teaching this class is just a huge privilege of mine, and it's nice being in the same room with you all. Some days I wake up and just feel like expressing that to you. So we have okay, moment of earnesty over. We're now going to talk about some economics. So we've basically 3 key questions. One is, what are the main challenges with working with time series data? How do we actually analyze data that's related through time? So I'm going to give you some pictures for why this stuff is hard. And then how do we sort of extract seasonal patterns? So if there's, I buy more things on Amazon in December than any other month. This happens for most people every year, and Amazon knows this. So we want to understand not just the trends in Amazon behavior, but also how do we sort of de-seasonalize, pull out the pattern that I buy more things in December? How do we control for that? So we're going to talk about seasonal patterns. And those are the 2 big things, and we're going to try to do it all using the general linear model. So kind of 2 separate ideas, all under the umbrella of time series data. This is a big one, or at least it's fun. We're now in the part of the semester where we can actually work with true-to-life, real economic data. All right, so you all have seen a picture that looks something like this, right? This is often the thing, even in high school, you've probably seen a picture that looks like this. We have some value on the vertical axis and then time on the horizontal axis. And, we're thinking about something through time. That's the basic picture. But you may have noticed part of the problem already with when we're working with data that's related through time is each data point. So this first one is more closely related to the second one than it is to the data overall. We have this correlation between data points in sequence. So a data point tomorrow is more closely related to a data point today than it is to just the data in general. We have this correlation between data points, this relationship between data points related in time. This is what we call autocorrelation, sort of auto just being sort of self-referential. So we have this data problem where the sequence is more closely related to the data before and after it in the sequence than it is to the sequence overall. And I'm going to show you a picture of why this is a problem in a second. We sometimes call this serial correlation. It's like the Fruit Loops are clumped in your bowl. Serial correlation, anyone? Okay, third time I've tried that joke. It hasn't worked at any of the 3 times. Going in the dustbin of history. So we're just going to define autocorrelation and then show a picture of what it looks like. When we have data that's in sequence, we talk about autocorrelation just being that, data points are more closely related to each other than to the sequence overall. And the picture we can draw looks something like this. So let me just talk you through what this is showing us. On the horizontal axis, we have yesterday's value, so the previous value in sequence. And then on the vertical axis, we have the current value. So I'm just taking for every row, I'm just taking that value, and then I'm plotting it against the row below it or above it, depending which way we're going. And the problem here is that when we randomly draw a data point, we are, the distribution itself is centered on the data point that came before. So what we get are sort of correlated movements in our data set. So if I draw the current value today, it's going to be very closely related to the data point before. So just in our data, you can see GDP values are very similar quarter after quarter, which tells us there's the possibility of autocorrelation in our data. Okay, so this is just the picture. If I were to simply take a regression equation and run a line through this, so I have our time series data, which is autocorrelated, as we just showed before. So each data point is very closely related to the data point before it. I can fit a line through this. And I can do this, right? We can just try to predict whatever the y variable is using time as our predictor variable. So I have, let's say, GDP as our output variable. I have a vertical intercept beta 0. And then I have a slope coefficient on time itself. I can just draw a line, and this will return an estimate of the relation, sort of the change in our y value through time. But if we run this, even though we return an estimate of beta 1, the p-values will be wrong. One of the assumptions of OLS, we talked about 4 of them. The second assumption is independence of the data. So every time we take a random draw, for the model to be correctly specified, for the p-values to tell us precisely the probability of seeing our data given the null hypothesis, for that p-value to be correct, we need that the data is not correlated in time. So the sequence is not dependent on what came before. And what you can see here, what I have in the first figure is our standard residual plot. And this has some problems. It looks maybe fine. But what we can see is in this second plot, where I've taken the residual in the previous period as the horizontal axis, and then the residual in the current period as the vertical axis. You can see that my model is making mistakes in ways that are correlated. And this means that our p-values are uninterpretable. We can't interpret the p-values associated with this model because we have autocorrelation. So what we end up having is a model that will give us a beta, like an estimate of the coefficients, but we just can't use the p-values. So this is a problem if we're trying to make claims about the probability of being wrong. If we're trying to test a hypothesis of what beta 1 is, the fact that we don't have correct p-values means we can't make statistical claims. So this problem of autocorrelation may feel in the weeds, but this is truly a problem, and we need to address it if we are to make probabilistic claims, statistical claims about our estimates. If we're going to do any hypothesis testing, which we've just spent a considerable amount of time walking through, we have to fix this problem of autocorrelation. And today I'm going to give you one of a couple of approaches for making this problem better. And we're going to do this with GDP and unemployment data. Okay, so this is what I've sort of talked about already. When the error terms are serially correlated or autocorrelated, we violate the regression assumption. And you can see why this is, because the error terms are correlated. So this random draw from our t-distribution is not happening. There's no underlying random variable that we're drawing from over and over again. We're drawing from different t-distributions each time. And that's a problem. Okay, so what we're going to do, instead of running this levels regression, we're actually going to run a differenced model. So to show you this, the first thing we're going to do is actually open some data, work with Fred data, and then we're going to build the difference model. Do you all have interest in working with some macro data? Yes? I'll take that as a yes. Enthusiastic yes, I love that. So in this notebook, which you should be able to find on the part 5 page, if you click on this, it'll bring up the notebook. Should we call this Gosling's law? Okay. Actually, no. How do we spell Ryan Gosling? Or not Ryan, Gosling. Anyone know how to spell? Yeah. Okay. I can do every level of calculus and all the data analysis you want, and I still can't spell someone's name. Don't ask me how to spell Corin. Okay, so we'll call this Gosling's law for today. So what we're going to do is just work through some data. So if you go through to the Federal Reserve, you can click on this link here, and that'll bring up the Federal Reserve data. And this is just a huge data set, or a huge database of data sets you can work with and just download directly. So what you could do is just, GDP is just one of the first ones here. What we actually want is real GDP. So this is like accounting for inflation. So you can click on this and it'll just bring up a list of different data sets you can work with. So gross domestic product per capita. But the one I'm working with is gross domestic product. So you can just click on this and it will give you like not only a picture, but you can also download the data as a bunch of different formats. So the one I like the best is CSV, which is what I did. The other data set we're going to work with is unemployment. So you can click on this, unemployment rate, unemployment level. So this is the one I worked with. So you can download this again. You can just see that the unemployment rate as a percentage. Okay, so this is the data set, and this is actually like literally what I did in my office. I just downloaded these data sets and put them in my Google Drive folder. Okay, so the first one, if you're loading the uh, real GDP, like the one that's controlled for inflation. This is there's this way of calculating real GDP using a chained inflation adjustment procedure. So this is the way what the data is called is GDP C1. So it's like a way of adjusting for inflation. So I'm just going to load this, and you can see the two columns. We have the date, and then we have the GDP value. And then we can also load the unemployment rate. So this is observation date. So again, this is like the same date. The dates are a little bit different. Like GDP starts a little bit earlier, but that's not a problem. And then we have our unemployment rate. So this just tells us the unemployment rate in that quarter. So then the next thing, I wrote a bunch of code here just to process these things. You're going to have to do some of this when you're working with your final project. But this basically just merges the two data sets. So we have unemployment and GDP. And so what I'm doing is just merging them into one data set using the date. So if there's the same date in both of the data sets, I'm just going to create a new row with both of the columns. And I'll show you a picture of this in a second. And I did a bunch of other things constructing different variables. But this is what it looks like. So we have our observation date, we have GDP, we have unemployment. And then I just created a variable called quarter, another variable called year. Time is just the year as a year and quarter as a real number. So this is like the second quarter in 1948. And then I have a base time. So this is basically the number of years since our base year. We'll talk about why we do this a little bit later. And then I've constructed some measures of like change in growth rates and such. We'll talk about all of this when we get there. But if you want to just download this data set, you can find the data set in its raw form on the Part 5 page. It's just, I called this ECON.csv, so you can just download this and get the data set I've constructed if you don't want to go through this work. But it's good practice if you want to just go to the data directly, giving you all the tools with the source to be able to construct this yourself. Okay, so the first thing I'm going to do is just plot the GDP against time. So this is just a picture. This is like raw data from the Federal Reserve. This is the data we use as economists, like just straight from the source. And you can see a few things. So this is the Great Recession, right around 2008. And then this is COVID, just a massive drop in GDP. And you can just see this directly in the data. You can also see this is not linear exactly. So the first thing we're going to do is run this basic levels regression. So I'm going to try to predict GDP using time and a vertical intercept. So I have GDP as our y variable, and then I have base time as the time variable. So when I run this, I get a model that looks something like this. So someone tell me, does this look correctly specified? Does this look like a good model?
Yeah, I think it looks like a good model for this data, but I think as soon as like it goes on and on, we can worse of a model if we're just evaluated on this. Like this with the model we keep with, it looks like it's just slowly going down.
Yeah, we have like basically an exponential relationship, right? GDP doesn't scale linearly, it scales multiplicatively, right? There's a growth rate, and then that growth rate kind of compounds. So GDP being estimated using a linear model may work in certain local areas in time, but it's not a great model if we're looking at long-term growth. So we need to probably do something different. But I'm going to show you a couple other pictures just to confirm that this is not very well specified. The first one is just our residual plot. So how does this look as a residual plot? This is about as bad as it gets. So this is a first indication that running a linear regression model, trying to predict GDP using using time as the predictor variable, is just not the right thing to do. So this violates a couple of assumptions. First off, violates the assumption of linearity. This is not linear residuals. It also may violate heteroskedasticity or homoskedasticity, but it definitely violates linearity. But like I showed you in this picture, we can also check for autocorrelation using a lagged residual plot, like this one. So we look at the residual from last period against the residual from this period. And that picture looks like this. So I have the current period's residual and then the next period's residual. So I'm going to shift all of the data by 1, and then we're just going to plot this. So does this look like the error terms are correlated? I don't know if it can get any clearer than this. This tells us that we've violated assumption 2 of OLS, which is that we need the error terms, we need the data points to be uncorrelated, so independent from each other. Okay, so not a good model. And you might be able to recognize this simply by looking at this figure. This is not a good model. A misspecification happens in the same direction for all of these values in series, in sequence. And then the same for old periods, and then for very recent periods. Okay, lots of problems. So what do we do about this? Well, I've already hinted that we might want to use differences. So instead of thinking about the actual values themselves, one thing we often do with time series data is take a difference between two periods. How many of you have seen this done before? Using a difference model? Yeah, maybe. And in your macro classes, you've probably seen figures plotting growth rates and not actual GDP. So that's going to be part of the approach we take today. So you can look at these two data points, these first two, and you can see the first one is higher than the second one. So if we take a difference between those two, we end up with a negative value for our difference. Basically, the size and direction of the slope between each of the data points. And so you can see the first one, the differenced GDP is negative. And that's because this direction is down. So if we're just plotting levels, we can see the change in GDP as just the slope between any two data points. And then we just plot the size and sign of that change as a data point itself. So this one's a little bit negative. The second difference is positive and a little bit bigger. So you can see this second one is positive and larger in magnitude. It'd be a little tedious to go through all of these things one by one. We have computers to do this for us. Thankfully, we don't ever have to write out differences by hand. Maybe that's the moral of this class. Let a computer do it for you. So all I'm going to do is construct the differences in GDP. And what I've done here is plot all of them against time. So this is a question for you. If you were to construct a linear model predicting change in GDP using time, what would you expect the beta 0 coefficient to be? Just using this picture. The intercept term for the second, for the green model, for the difference model. Yeah, it's maybe a simple question, but I'm looking for an answer. Okay, no one? 0. The answer here is 0. The intercept term on this model would be 0. We're trying to predict the change in GDP using time. The vertical intercept is going to be 0. And then the slope will probably be roughly 0 as well. So it's like no slope and a vertical intercept of 0. And so in this case, when we look at the difference model, looking at the data of plotting the differences, we would correctly observe that there's basically no relationship with time. Okay, so I'm going to give you a second question, and you're going to tell me a slightly different answer. We're spending a second talking about this because the intuition matters for how we interpret the regression results I'm going to show you in a second. So I need your attention. So what if we had this one? So on the top figure, I have just base GDP, so our Y variable. And then on the bottom, I haven't plotted the figure for differences. And we're going to construct this. You're going to tell me what you think that data might look like, and then you're going to tell me what the estimates might look like for a regression model through that data. Sound okay? So the first figure, we have, I mean, this looks like it's increasing, right? So each of these differences will be maybe positive. And even though it's, it looks pretty linear, there's still maybe a little bit of variation in each one of the slopes. So someone tell me, what do you expect this figure to look like? We have delta y and we have time. Garrett.
Well, it's probably just going to be some variation that's going to be above zero, like above 0 the entire time. This is always been constant.
Okay, so it's going to be, so Garrett's saying,
Down, down.
so some variation up here, it'll be probably flat or potentially flat.
Yeah, close to that, probably not going under the change in y, but it's never going to be negative.
So probably not negative, probably positive the whole way. Yeah, is that what you're going to say, Luke? Yeah, nice. So what if I gave you this? Okay, yeah, so maybe Garrett's hypothesis is wrong for one data point, but basically true, right? Basically variation around some intercept term, but it's basically all going to be positive. Okay, so second question for you. If you were to estimate a regression model, what would you say the beta 0 would be in this case? Just a rough estimate of what the beta 0 would be. Around 2. So maybe right around here. So we just draw a line, and then it'll hit 0 right around 2. And then maybe 0 slope. So I've given you two examples. The first example, we have basically no relationship with time, and our vertical intercept is 0. So no slope in the original data and a 0 intercept in the differenced data. But then in the second example, we have a positive slope, which I'll tell you is a slope of 2. And then the vertical intercept of the regression model through the differenced data has a positive intercept and an intercept of 2. All right, so we're going to run a regression, and you're going to tell me what's going on here. But the basic idea is once we turn to differences, the vertical intercept has meaning. It tells us the slope of the original data. So how GDP is changing. So what we're going to do is run a model predicting GDP using time. And then what I've done here is plotted some residuals. So with our differenced model, our residual plot looks much nicer. This is beautiful to me. And we can also see with our autoregression residual plot, we don't see the kind of autoregression that we did earlier. Like this doesn't look highly correlated. This doesn't look like the error terms are related to each other, which is much better. Okay, so here's some code to run some of this, but I'm going to hop over to the notebook and plot these things. So what I've done is constructed a GDP difference. So in the original data, what I did is construct GDP diff, which is just GDP in one week or one quarter subtracted, and then I've subtracted the GDP in the previous period from the current period, which gives us GDP difference. So it looks like this. I've also done the same thing for unemployment, so just the change in unemployment. And then I've also constructed a GDP growth rate, which we'll come to later. So what I've done here is I've just plotted GDP difference against time. So this is just the picture of GDP through time. Anyone know what this is? Yeah, a huge outlier. Like we've just never seen anything like it. A massive drop in GDP in one quarter and then a huge rebound in the next one. Basically because we shut everything down. So this is not a very common scenario. So what we can see here, a couple of things, looking at the GDP difference data, as you can see, there's less variability at the beginning. So the variability down here is very low, but then the variability up here is pretty high. We also see COVID, which has this huge spike. What I'm going to do for our purposes today, because it was such an outlier, I'm actually going to filter out all of the data up to 2019, or filter all the data after 2019. So we're only going to include data up through 2019. And what this looks like is this. So this is a little bit more normal. We're throwing out the outlier. You can quibble with why we're doing that, but it's going to keep our analysis a little bit simpler because there's a bunch of other stuff that happened with COVID. And so the question we might wonder about is whether we can find the growth rate, or the growth, the difference in GDP over this period. So what's the average? So the average change in GDP quarter to quarter. So what I'm going to do is just construct a linear model where we try to predict GDP difference simply using an intercept term. So this one is just giving us only the intercept term. And you're going to interpret this model. Okay, so we're going to take like 30 seconds to a minute here. I want you to tell your neighbor how to interpret what we see here. Maybe tell them something funny you're going to do this weekend, and then tell them how to interpret this regression model. Take about a minute. Go. Okay, someone help me out here. How do we interpret this? Sorry to interrupt your conversations. It sounds lovely. How many of you had a correct interpretation, or what you think is a correct interpretation? Hands up. No one? Okay. Or are you just not answering my question? Should I interpret this and then you'll do the next one? Or, yeah, Luke.
So the coefficient 65.3 something, that's kind of like the initial value, or kind of like our beta 0 value for
Yeah.
the regression line. And because the p-value is apparently very, very, very small, it is very unlikely that that would happen due to random chance, so we can say that this was significance.
Yeah, so essentially we have an intercept term only. We see that this is we're very confident this is not zero. Because we're looking at the difference in GDP, what we're saying is with this intercept term, we're very confident that the economy is growing. Our best guess would be that it was growing $65 billion per quarter. This is beta 0. So beta 0 in this case is our intercept term, which tells us on average how GDP is growing, because this is GDP difference. So it's how GDP has changed quarter to quarter, and on average, that's $65 billion. Okay, any questions here? All right. So the next thing we'll do is include not just an intercept term, but also a slope term. So I'm going to run this, and then I'll plot the model here. So here we do have an intercept, but then we also have a slope. So someone, should we take a couple minutes here? Or like a minute? Do you like talking to each other? It seems like you do. So let's take a second and try to interpret what's happening here. All right. So I gave you the interpretation for the last one. Someone tell me how to interpret this one. What does this intercept term mean? Ben. This is our beta 0, yeah. And what is, how do we interpret the beta 0?
Whenever the time increases by the quantity amount, that's how much the intercept increases.
Okay, so we basically have this this intercept term which tells us the GDP growth in our base year. So like when the data starts. And then what Ben's also pointing out is our time variable also has a positive coefficient, very significant, which tells us that we have a slope. And what is this? If you were to summarize all of this, all of Ben's interpretation and our figure with our coefficients, how might you say what we've just found? Yeah, Dom.
For every 1 year, our predicted increase in GDP would be 1.27, starting from the base year, which would be at 19.22 million.
Okay, yeah, so our GDP is growing, and every year it's growing faster. Or every quarter, I guess. Every quarter it's growing faster. Was that a summary of your interpretation? Yeah, nice. So in like roughly 1950, GDP was growing at $20 billion per quarter. Every additional quarter, like as time goes on, GDP grows faster. Okay. Any questions here? Okay, so we've looked at the problems with levels regressions when we talk about autocorrelated data, and then we've gone through and plotted the autocorrelation, and then we walked through an example here. This is just a really simple example, and we showed that taking first differences actually removes a lot of the problem of autocorrelation, and we can see that in the autocorrelation of residuals. We can check this in our real Federal Reserve data. So this was our model. What I'm going to do is just plot out the residual plot. How many of you like this one? Does this look fine to you? Or are there problems? Just our residual plot. So horizontal axis is our prediction, and then vertical axis is our residuals. Yeah. Yeah, it's violating. Yeah. So we have a violation of homoscedasticity. The variability in low values is much smaller than the variability in high values. So we're going to come back to this problem. But to me, this looks better than our first residual plot, which was this one. This is just horrendous. The second one is a lot better, this one. We're going to fix this problem of heteroscedasticity in a second. And then the other thing we can do is just check for autocorrelation. Does this look like autocorrelation or not? I think this is better. It looks a little more random. It doesn't look like there's a clear slope here. Like it may be positive, but it's not so clear. The last one, if you remember, looked like this. We fixed this problem. Like we're way better than this. Just like my high school cross-country coach told me. All right, so we've built a better model, and we've built it using differences. We've removed a lot of the problem of autocorrelation simply using first differences. It hasn't fully eliminated the problem. We can't simply get around the problem of autocorrelation using first differences, but it at least gets us in the ballpark of something that's better. The next thing we can do is actually relate two time series variables with each other. So what we've done here is we've plotted the difference value over time, and we've used time as our predictor variable. But what we can also do is think about two different variables through time. So on the vertical axis, I have the difference in GDP. And then on the horizontal axis, I have the difference in unemployment. This is a simulated figure. This isn't our real data, which we'll get to in a second. But this is one of the things we can do, is run a regression predicting one time series variable against the time series, another time series variable. Just link them in time. So each one of these data points represents a change in unemployment against a change in GDP. And again, we're removing these spurious correlations because we're taking differences. Beta 0, like before, captures the same intuition as it did when we were talking about time. This is just the average, sort of the sort of middle point of our change value. And then beta 1 captures the relationship between the different variables. So what we're going to do is run this kind of regression. So I have unemployment against time. So we can plot unemployment against time. So that looks like this. And then we can also look at the difference in unemployment. So the change in unemployment quarter to quarter. And that looks like this. So we can see sometimes we have negative change values and sometimes we have positive change values. Okay, so we have this is our delta X, and then we also have our delta Y, which is our GDP difference. So what I'm gonna do is just run a regression model predicting change in GDP using an intercept term and change in unemployment. I'm gonna plot this. So it looks like this. So on the vertical axis, I have change in GDP, and then on the horizontal axis, I have the change in unemployment. So again, we're gonna take a second here and interpret what this is telling us. So we have our nice regression model telling us some numbers. We've plotted that regression model against the base data. Someone interpret what's going on here. Let's take a minute, tell your neighbor what the interpretation is, and then we'll talk about it together. Okay. For the sake of time, we have like 2 more models to get through. Someone tell me how to interpret what we're seeing. Yeah.
Unemployment has an inverse relationship with GDP. So as unemployment decreases by 80, GDP increases by 65.
Almost. We're getting pretty close. Someone make a correction here. We have a roughly 80% decrease, a negative coefficient of roughly 80. Someone reinterpret what that negative 80 means. We know that the change in GDP is negatively related to the change in unemployment. So these two things move opposite with each other. Luke.
So unemployment increases, GDP tends to decrease by approximately 80. So every change in unemployment.
So when unemployment goes up, GDP is lower than it would have been before. So we have a negative relationship between unemployment, the change in unemployment, and GDP change. Part of the complexity here is we're talking about not levels, but changes. And so it's a little bit harder to interpret these things. So basically, as we increase unemployment, that tends to lead to lower GDP. but we also have a beta 0. So we can't say that that GDP will go down when unemployment goes up. What we can say is that it would be lower than if GDP was, the unemployment rate was, had decreased. Okay, so part of the thing here is interpreting these models when they're correctly specified using differences like this is actually just harder. It's harder to do. All right, so if there's no change in unemployment, if unemployment stays the same, then on average, we see an increase in GDP of roughly $65 billion per quarter, with no change in unemployment. But then as we increase unemployment, each 1 unit increase in unemployment, 1 percentage point increase, leads to a smaller GDP. All right. Any questions here? So what do we do next? Someone tell me. We've run a model, we've plotted the model, we've interpreted the model. Let's check that the model assumptions are sound. So what we're going to do is, I guess I don't have this in the slides, in the notebook. But what you could do is plot the residual plot. So we're going to plot the residuals. What do you all think of this? Fine. Not great, maybe, but fine. And then we can also check for autocorrelation using our lagged model. So this looks fine to me. This is maybe positively autocorrelated, but this looks fine. This is way better than our first one. So what we've done is, we've related 2 time series variables together. So it's not just looking at, a path through time, but we're actually, the horizontal axis here is not time anymore, which allows us to look at relationships between multiple variables in time. And then we can check the model assumptions. And the interpretation is often harder in these cases, which is fine. We just need to be clear when we're doing the interpretation to be able to write it all out. So I will ask you some more questions about that in coming assignments. The last thing, and I want to take your attention back to one of the figures we were looking at before. So you remember this figure, the residual plot for Model 2. And remember we said we had a problem of heteroscedasticity. Wow, really tough crowd. So we had a problem of heteroscedasticity where the error term has much smaller variability with low values and much higher with high values. And I want to point your attention to this picture. When we have something like GDP, which scales with time, as GDP gets larger, a change in GDP becomes less important. So if GDP were to go up 40 billion between 2 quarters, in the US, that's pretty normal. It may even be small. But if the country is like Thailand, I'm thinking about Thailand because I'm watching White Lotus. In Thailand, an increase in the GDP quarter to quarter of $40 billion would be massive. So the increase, the delta, the difference between 2 quarters GDP, depends on the scale. You'll remember in your macroeconomics class, you talk about elasticities, or we do this in intro micro too. Elasticities, it's the percent change in some variable, so the growth rate. When we see a picture like this, something like GDP, if we simply look at differences, we end up the difference in levels. We see small changes early on, but then as GDP scales, we end up seeing much more variability later on, simply because the scale has increased. So not only the differences have increased because the base scale has increased. So we get this larger variability in the differences. And this led us to the problem of heteroscedasticity in that picture from before, in our differences model. So what we do instead is we look at growth rates. So instead of just looking at the difference between two values year to year, we're actually going to divide it by the base year. So we not just look at the difference, but we also divide by the base year. So instead of looking at the deltas like we've been doing, we're going to divide by the level as well. So this gives us a percent change, which is how we define a growth rate. So what we can do is look at growth rates both on the vertical axis and the horizontal axis. And then we can just run regression models on this. So we built up step by step. This is our fourth model. We're now using growth rates. Let's turn to some data. So we'll run a regression very similar to this. I'm going to make one change to get us Oken's law, but this is going to be our approach. And we'll come back and summarize this in a second. All right, so we had our third model from before, where we got a negative relationship between the change in unemployment and the change in GDP. But we know GDP scales, so let's convert GDP into something that we can deal with that's scale independent, like growth. So we're going to use the growth rate. So if I plot the growth rate like this, you can see there was much more movement in the growth rate early on than there is later. But this gives us a scale independent variable. So what I'm going to do is plot the difference in unemployment on the horizontal axis, and then GDP growth on the vertical axis. We'll just plot this. So this looks pretty similar. But instead of looking at the difference in GDP on the vertical axis, we're now using growth rates. So it's been normalized to account for the scaling property of GDP. And then what we're going to do to be consistent with Oken's law is I'm going to use unemployment as our outcome variable, and then use GDP growth as the predictor variable. So this is Oken's law. Maybe just a picture, but this is a standard picture of Oken's law, where we have GDP growth on the vertical axis and then unemployment on the horizontal axis. And so what I'm going to do is just run this regression. I'm going to plot our model, and then you're going to tell me whether this is consistent with Oken's law. So let's take about a minute here. Tell your neighbor whether you think this is consistent with Oken's law or why it's not. And then we'll come back together and make some conclusions. And in your conclusions, I'm looking for an interpretation of these values. We're in a world where it's much more difficult to interpret the betas because we're talking about growth rates and differences. But this is something we do need to do. It's harder, but it's more important. Okay, someone help me out here. Is this consistent with Oken's law? Yeah, just look at the picture. It's like we have a negative relationship here. Someone interpret what these values are doing for us. Pictures are part of the reason we use visuals is because it's often very easy to interpret what the visual is telling us. A scatter plot is worth 1,000 words. I think that's what the old saying, how it went. What's going on here? Someone tell me some numbers. Yeah, Luke.
So as the unemployment rate increases, or the change in unemployment rate increases, GDP tends to decrease along with it.
Okay. So GDP and unemployment, so GDP growth and unemployment, change in unemployment are negatively related. Yeah. So another way of saying that is higher GDP growth leads to lower unemployment rate. So or it leads to a decrease in the unemployment rate. Okay. So we also have a vertical intercept. So just our base level of unemployment with no GDP growth is positive. That's what this would tell us. The vertical intercept is positive. So our base level of unemployment is of change in unemployment is positive. So unemployment goes up when we don't see any GDP growth. Okay. Any questions here? This is probably the hardest interpretation of a regression we've seen so far. But I'm going to make it even harder. Sound fun? In the last few minutes of class, I just want to present to you a slightly more complicated problem. So I spend more money on Amazon in December than any other year. I haven't actually checked this, but I'm pretty sure it's true. And most people do. We see cyclic patterns in so many things. We buy, holiday cards in December when, I've just never thought about doing it in March. So we see lots of patterns like this where, depending on the quarter, we see higher or lower values. And so the way this shows up is, something that looks like this. So we have many years, and then we have this seasonality pattern. So in the third quarter, we tend to see higher values. So whatever this vertical value is, we tend to see higher values. And you can see that in all of these different years. This is a consistent pattern, but we might not care about the pattern in seasonality, and we might be interested in just, is there an increase in the data itself without accounting for the pattern, or without being interested in the seasonality itself? Is there some underlying pattern deeper than this seasonality? And what I'm going to show you is we can actually deal with this problem of seasonality using fixed effects like we did last class in our general linear model. I'm going to include a fixed effect for every one of the seasons, every one of the quarters, which will leave behind it just the core pattern. So we can see here is I've broken the data into 4 quarters, so each one of our quarters, and just plotted the average value. And you can see this is another way of seeing this seasonality thing that we see in the time series data. So we see a spike in Q3. And what we want to do is sort of account for that spike while still leaving the trend. So I'm going to switch focus from looking at one variable in time to looking at 2 variables in time. But as we make this transition, I want you to be thinking about the original data, which looks something like this, broken into 3 parts. We have our trend piece, so just how does the baseline in the data look, we have our seasonal component, which are these like regular ups and downs simply due to the season and not due to the trend. And then we also have our residual component, which is just the error, like the sampling error. And these three components make up the original data. So we can just add these together to get our original data. And I'm going to try to convince you in 1 or 2 slides that this is actually something worth doing. So I have this picture here. I have 4 quarters of data. And when you see this picture, you're thinking, okay, I'm going to draw a line. Like if I'm trying to predict our y variable with our x variable, I draw a line through this data, through all of these points, and that line will look something like this. Right? That's just a model with only one intercept and only one slope. As we do this, I want you to think back to what we did last class with this. We had 2 intercept terms. One was our intercept, one was our binary indicator variable. We also had a slope. Here, we can do the same thing. And what I'm going to show you is a picture where the slope is very different when we include 4 different intercept terms. So it looks like, I know what time it is. Looks like this. I would say this is highly unintuitive. But once we include 4 different intercept terms, one for each one of the different quarters, we end up with a slope that would not be how we would fit the data without 4 intercept terms. Right? The original slope you drew was steeper. But because we've allowed for 4 separate intercept terms, we actually get a more precise and more correct relationship between our x and our y variables. And we can do this in code very simply. This will be the last thing I show you. But what I've done is I've broken out GDP growth into 4 quarters. This doesn't look quite as pretty as the figure I have in the slides. But what I'm going to do, so we have our regression predicting unemployment, the change in unemployment using GDP growth. But what I'm going to do is include 4 separate intercept terms for each of the 4 quarters. So there's the syntax C, and then I'm putting quarter, which is a categorical variable, into C to give us 4 separate intercept terms. And when I run this, it allows me to compare baseline unemployment differences by quarter. So I get 4 different intercept terms for each of the 4 quarters. Different intercept terms for each of the 4 quarters, just like this picture, which allows me to compare baseline unemployment by quarter while still controlling for GDP growth. Okay, so we'll leave this here. Next time, we're going to start talking about how we separate causality from correlation, which is a big topic. I'll see y'all next time.
So is the first quarter the intercept for beta 0?
Yes, exactly. And then T2 is, we have quarters listed out as 1, 2, 3, 4. So T2 is the second one. Yeah. Yeah.
If you find something that's like,